Funciona? Ah, sí, sí que funciona. Okay. Okay, good morning, everyone. Well, it's a great pleasure to introduce you Francisca Kemper, Siska Kemper for short. She did the PhD in 2002 at the University of Amsterdam, and after that she moved at the UCLA as a Spitzer Fellowship. Of course, she got several faculty positions around the world, and including Taiwan, where she stayed several years, almost 10, yeah, okay, 8 years. And there she was actually involved in several projects like ALMA. And 2018, then probably no, she got the position as an European ALMA program scientist, right, at the ISO here in Garching. Well, here not, but close in Garching. Well, compared to Taiwan, it's here, Garching, of course. And well, now last year she got this ICREA research professor position at the Institute of l'Institut de Ciències de l'Espai in Barcelona. Well, she has been working for several years investigating the dust properties, the formation of dust particles in the interstellar medium, and the evolution in galaxies using far infrared, submillimeter observations, and with the main goal to determine the mass determination of different redshifts, no, for these galaxies. And actually, no, today she's going to present us to talk about the interstellar dust reservoir in galaxies. Thank you very much and welcome, Siska.
Thank you, Gemma. Okay, thank you, and good morning, everyone. So yes, indeed, I joined ICEA 1 year ago as an ICREA research professor, so I'm still new. I'm here to the local environment, and apart from presenting today to you what one of my research interests, I would also like to point out that I'm looking for local collaboration, so if anyone is interested, we can talk afterwards. So please keep that in mind if you see something of common interest. So when I talk about the interstellar dust reservoir in galaxies, we are basically looking at a number of different aspects that are associated with the life cycle of dust in galaxies. So here in this diagram, you see sort of this darkish cloud in the center, which represents the interstellar dust reservoir that we're talking about. But out of this reservoir, or the dust in this reservoir, is being consumed in processes of star formation. And when you have star formation going on, you can either form low mass stars or high mass stars, or a mix of the two. Of course, high mass stars, they evolve rather quickly and with an explosive end, creating compact objects like this. But the majority of the material gets returned to the ISM, and including a dust component. The same for low mass stars, but it just takes, the evolution takes longer. The mass loss at the end is less explosive and more gradual. But again, gas and dust is being returned to the interstellar medium, and a shell, not a shell, a compact object remains here. Now, why do we want to study dust in galaxies? So this is sort of the background of this talk and the work that I do in general. Well, first of all, dust, it is only a minor component. So why would you actually want to study it? It's only 1% of the interstellar dust mass. Interstellar mass, sorry, it says dust mass there. The interstellar mass is in the form of dust. However, it reprocesses starlight, and therefore it is an important factor in galaxy evolution. So here, this diagram here, this blue part, shows the spectral energy distribution of starlight, so the shaded area as well. Then if you insert dust in a galaxy, this light here gets absorbed, the dust gets heated and reprocesses this energy that it received from the stars, and it gets emitted as thermal emission here at longer wavelengths. And typically, even though only 1% of the material in the interstellar medium is in the form of dust, about 30%, or in some extreme cases, up to 90% of the energy of a galaxy comes out as thermal emission in these long wavelengths, thermal dust emission. Dust is also a catalyst for chemistry. It particularly plays a role in the formation of important molecules like molecular hydrogen, which stands at the very beginning of the chemical network that then causes or leads to the formation of more complex molecules. And molecules are essential for star formation to actually proceed. And then finally, I'm actually, for this talk at least, interested in talking about interstellar dust masses, which are used as a proxy for star formation rates, especially in cases where we don't have any other information. So, wait, what? Are we really using interstellar dust masses as proxies for the star formation rate? And we do this actually by measuring submillimeter fluxes. For instance, using the James Clerk Maxwell telescope, where you have the Scuba 2 instrument, which has a 450 and an 850 micron receiver, and the 850 is particularly sensitive to seeing the thermal dust emission. And indeed, in many cases, especially for distant galaxies, there is a straight correlation, or at least it's presented like that. We measure a 850 micron point, and we get the star formation rate. But in reality, the thought process goes something like this, actually. We measure this 850 micron point. We then get an interstellar dust mass. Then we assume a gas-to-dust ratio, and you get an interstellar gas mass. Then we assume a star formation efficiency, and you get a star formation rate. So there's a lot of assumptions in here. And in this talk, I will focus on how you go from measuring this submillimeter flux value to an interstellar dust mass. And I won't go into these steps, but they have huge uncertainties as well. So let's talk about how you can measure dust masses. And for simplicity, let's talk about a number of different regimes that we can consider here. So the first one is the UV optical and infrared in absorption. So there we basically use the interstellar extinction curve here. There's just one example of what that looks like. If you work in the optical, you know here B minus V that you use, that you measure the reddening. You can actually use that information to measure dust columns towards stars in the solar neighborhood. This is a map out to 3 kiloparsecs showing the dust density in every direction from the sun. And the advantage of this is that if you have a background star, you see all the dust towards this background star. The disadvantage is that you can only sample towards certain background stars or towards background stars. If you don't have a background star, you cannot sample the dust in this line of sight. Then in the mid-infrared, you start, especially if you're talking about hot dust, you start seeing thermal dust emission. So this is the case when you are talking about circumstellar dust. This actually starts to emit at mid-infrared wavelengths, and then you're no longer limited to a sight line towards a particular background object. Instead, you can see all the dust that is thermally emitting. You can then fit a spectral energy distribution and try to derive the dust masses that way. And then in order to do so, you use dust opacities along with a dust radiative transfer model to figure out the dust masses involved. And then finally, if you are looking at even longer wavelengths, you're tracing colder dust, and you can measure the dust masses in the ISM. And then I'm talking about the ISM of clouds or perhaps of entire galaxies. And but you can see already in this diagram that towards the longer wavelengths, these these different measurements or these different determinations of opacity start to diverge, and there's also not much structure. So it's actually a lot of uncertainty once you go beyond about 100 or so micron, and we don't really know very well what's going on with the dust opacity. And people approximate this by using some kind of function for the dust opacity, which is, well, the kappa lambda here, which has a beta in there, a slope. That's here, it's not actually printed here. And if you have different values of beta, your shape of your SED looks different, and you will also get different dust masses just by having a different slope in the opacity. So in order to measure dust masses, dust opacities are key throughout all these wavelength ranges, but they're not necessarily consistent throughout the wavelength range, the entire wavelength range. Another thing to bear in mind that while we do know dust opacities well in UV and optical infrared, because we can go and measure them in the lab, this is a different matter when you start getting into the submillimeter and the millimeter, and we just don't know the dust opacities all that well. So continuing a little bit more on this aspect of dust opacities. So how we measure the dust mass at the longest wavelengths is by fitting an SED with a temperature, a beta, and a dust mass at the same time. And what we do is basically we take the dust opacity, which take this form. It's a kappa 0, or it's typically a kappa 500 micron, and lambda over lambda 0 to the power minus beta here. And you multiply that by a black body and by the dust mass to get a modified black body. And typically, we assume a single, or perhaps in a very good case, a few temperature components. And the reason for that is that you have, for each temperature component, you have these three things as free parameters. And typically, we only have a small number of data points in our SED, so you can only really fit a single temperature component. And there are even cases where even fewer SED points available, and beta and even the temperature may be fixed. And of course, the choice of beta is very, very important. So here this diagram shows that. It shows what happens. So beta is somewhere between 0 and 3, we know this. So 0, it's a pure black body, and 3 is very, very steep here. And this plot shows the emission from a column of dust for a constant column density, which is here normalized at this point here. And you see how much it changes and how much the difference is between 450 and 850 if you use Scuba 2. So the slope is different, but also the absolute values that you measure is very different. And this is actually Herschel data of the Andromeda galaxy, where we have at shorter wavelengths than this, but a number of data points, perhaps up to 5, and you can fit an SED in each point and measure temperature, beta, and M dust. And this map shows the beta in each point. And you can see that they report that beta is highest in the very central part and lowest at the outside. Now, one thing that I want to point out as well is that kappa is also, it's usually fixed, but you can think of it as one thing that can be scaled as well. And the kappas that people typically use are these colored dots here, and they're sort of on the low end of the range of values that has been reported in the literature over the years. So if you use a relatively low value for kappa here, your opacities are relatively low, and the dust masses that you derive will be relatively high. So this is something to bear in mind. So for nearby galaxies, what we find, so in this next section, I will already foreshadow that what we will find is that the dust production coming from evolved stars is smaller than the amount of dust that we find in the interstellar medium. And I'll illustrate this with the LMC, but we actually see this in a larger range of galaxies. But the LMC is such a nice laboratory to do this in. And in fact, we did a survey with Spitzer and Herschel called SAGE and Heritage for the LMC and the SMC, where we mapped both galaxies in their entirety using all the IREC bands on Spitzer, all the MIPS bands on Spitzer, and these bands here, these 5 bands here on Herschel. So we have this very detailed map of the Magellanic Clouds, both the LMC and the SMC, and we can identify stars and interstellar clouds in maps like this. So for instance, in terms of stars, we find some 8 million point sources in the LMC. So those are sources that are detected at 3.6. But not everything that's detected at 3.6 is detected at longer wavelengths. So if you go progressively longer, you lose more and more point sources. But yes, we find 8.5 million point sources at 3.6. And in the SMC, that number is about 2 million. And then we have the clouds in between the stars. So an important component of the stellar content of the Large Magellanic Cloud and the Small Magellanic Clouds, especially if we talk about dust emission, are the asymptotic giant branch stars. So what are they? Well, they are actually evolved stars. So here is a Hertzsprung-Russell diagram, and you have the main sequence. It's a very, very schematic drawing here. And you have the red giant branch here that we are familiar with. At the end of the red giant branch, the star falls back here to the horizontal branch and starts to move again up in this diagram towards the giant branch. And that's why it's called the asymptotic giant branch. It's because it's asymptotically approaching the giant branch here. And what's happening is, in terms of the star itself, you have a CO core, and then you have helium and hydrogen shell burning going on around it. So that's what's happening on the asymptotic giant branch. Your star actually itself is pulsating and rather unstable. And in this pulsating envelope, some gas gradually gets moved out further, and molecules start to form as the temperature starts to drop, because it's moving away from the star. So we're now talking about maybe 2000 Kelvin. At some point, the temperatures drop enough for dust formation to occur. So this is below 1500 Kelvin or even less. And once dust formation occurs, the radiation pressure from the star on the dust grains pushes the dust outwards and generates a stellar wind where the dust actually drags the gas along, and mass loss occurs. I have a two-sided part in this diagram. So here at the top you see oxygen-rich species, and at the bottom you see carbon-rich species. And this arises due to the initial chemistry of the star, where carbon over oxygen is either smaller or larger than 1. And whichever the case is, the one that's less abundant is entirely locked up in carbon monoxide, which is a very stable molecule. And then the other species is the other atom. So in case of an oxygen-rich star, oxygen is available to drive an oxygen-rich chemistry and form silicates. So what are the properties of AGB stars? So this will come back later, but something to bear in mind. Because they are solar-type stars, and at the end of their life, they have moved away from the site where they were formed, and they're relatively isolated, also because they're relatively few in number. They're also very bright in bolometric luminosity, and especially in the infrared, so you can easily detect them. And they're dusty. We assume they have a spherical geometry and that their outflows are constant. I will come back to this later. And I already talked about this. This diagram shows a spectral energy distribution of a particularly dusty AGB star. And you see here these features at 10 and at 20 micron here, that are the silicate features that are actually seen in absorption because it's very dusty. This diagram shows the distribution of AGB stars in the Milky Way, and you can see they're all over the sky, so this demonstrates this isolated part. Okay, so for the purpose of the SAGE survey, what we did was we calculated a grid of models. And here on the right-hand side, there is an example of a grid of models. This is not the grid that we calculated, but I couldn't find a nice overview picture of the grid that we calculated. But this is an example of what we might have done. So you basically take a dust radiative transfer model like this one here, 2dust, which is the one that we used, and you start increasing the dust mass loss rate. So here it goes from the gas mass loss rate, 2 times 10 to the minus 7 solar masses per year, all the way here to 10 to the minus 3. And as you increase the mass loss rate, you see that the spectral appearance changes because the optical depth increases. So we did something similar, and then you can calculate synthetic photometries along the SED for all these model grid points. And so that's what we did, and we did it for representative dust composition. So we isolated carbon stars and oxygen-rich stars. Here is a column magnitude diagram from the original SAGE survey, where we identified the different populations. So carbon-rich stars are sitting here, and different types of oxygen-rich stars that were tested, or that were actually identified using 2-mass photometry. For a tip, we also had some spectroscopy for selected object. That's not for everything. So we took a representative oxygen-rich star and a representative carbon star, and we fitted the spectrum. And then we used the dust composition that we derived from fitting the spectrum to build up a grid. So in this case, we built a grid of carbon star models, dust radiative transfer models, which consisted of 90% carbon dust and 10% silicon carbide dust. And also we made a grid of amorphous silicate dust models, purely 100% amorphous silicates, because that gives a nice fit here. And the results are shown here. So these are actually, again, column magnitude diagrams, different column magnitude diagrams, not the same. And you see that all the gray points in the background here and here are the grid points of the model grid, and the colored dots are the photometry from our survey. So they overlap, and we can then determine what grid point they fall closest to and determine the dust production rate, amongst other things. Okay, so indeed that's what we did. So we added up. Here is an example for a. This is a oxygen-rich object, and this is a carbon-rich object. We found the best fitting SED from the grid in both cases, and here is also an overview of the stars that were fitted. So here are the oxygen-rich, and here are the carbon-rich stars that are fitted. You see, they're not this. Here we have the same column magnitude diagram. You see, they're not actually the same population. So we first decided whether a star was oxygen-rich or carbon-rich using the color classification from 2-mass, and then we did the fit. And you can actually add up all these numbers because for each individual star you find a dust mass loss rate, and then sum the total. And we find, well, this table here, it doesn't really matter because you have to see this all in perspective, which I will show in the next slide. But we determined the dust production rates in the LMC and also in the SMC, which lays a factor of 15 lower. We also checked that our classification actually matched. So our color classification actually matched what we found from spectroscopy. And that indeed turns out to be the case. So here, we plotted with the larger symbols all the objects for which we have a spectrum, and that we could verify the nature of, and you see that they very nicely line up with the regions that were decided based on color codes. And we also had a whole bunch of objects that were not evolved stars, and they sit elsewhere in the diagram, so there isn't all that much interloping here. So then we looked at the interstellar dust masses, and again we did this by fitting in each pixel that we had for Herschel a modified black body like this, like I highlighted before. So a pixel by pixel SED fitting to derive the mass, the temperature, and beta in each grid point. And this map here is the LMC again, and disregard all the green, but all the color scale here is highlighting the dust masses pixel by pixel, so the relative dust masses. And if you add up all these pixels where we have enough signal to noise to determine the dust mass, we get to an interstellar dust mass of 7 times 10 to the 5 solar masses. And compare that with the dust production rate that was just calculated, which is a few times 10 to the minus 5 solar masses a year. Similarly to the dust production rate, other colleagues of us, other collaborators of us determined a star formation rate. It's a very similar process. Again, you compare what you think are YSOs with a grid of models, and they found a few times 10 to the minus 4, or almost 1 times 10 to the minus 3 solar masses of year in dust being consumed. So this means that if you compare those first 2 numbers with each other, the ISM dust mass and the dust production rate, you have a replenishment timescale, the amount of time that it takes for AGB stars to replenish the entire ISM of a few times 10 to the 10 years, which is consistent with the lifetime of the LMC and the age of the universe. That's good. And the astration timescale, so the timescale, the time that it takes for all the dust in the interstellar medium to be consumed, is actually much shorter, 10 to the 8 years. So if you just take a snapshot of the LMC today, you can already see that if the LMC continues as it is today, in no time at all, it will have consumed all its interstellar dust. And that actually, you should also actually realize that what we're not even taking into account dust destruction due to interstellar shocks or supernova shocks or dust formation. And actually, if you try to model this, so if you look at the dust production history in the LMC from a more theoretical perspective, and you take the star formation history as it has been derived, and you then do a stellar population model, you look at how many AGB stars are forming, at what time, using this star formation history model input, and what the yield is in terms of dust production from AGB stars, you get this curve. So this green band is roughly the production of dust over time in the LMC. And if you get to the very end, which is the present day here, there is a measurement here. That is the interstellar dust mass. So that is actually being measured here. And the production over time actually does line up with the present day dust reservoir. So that's what we just saw in the previous slide as well. But like I said, interstellar dust destruction is not taken into account. So you just reproduce all the dust, or you just produce all the dust that is present in the interstellar medium today, but you cannot have any dust destruction because then it falls apart. Additionally, if you actually look at all that output of dust, so this is a little sidestep, but something that we looked into, the LMC and even the SMC even more so, actually has a lot of carbon stars because of its low metallicity. This is an effect, a stellar evolution effect. If you have a dredge up in AGB stars, the star becomes more and more carbon rich over time. But because of the low initial metallicity of the LMC and the SMC, this is easier to achieve than in the Milky Way. So you have a larger number of carbon stars than in the Milky Way, and therefore the production of dust is actually predominantly amorphous carbon. However, the interstellar extinction curve in the LMC is very similar to the one in the Milky Way. So we think that the interstellar dust reservoir looks very similar to the interstellar dust reservoir in the Milky Way. And that one is dominated by amorphous silicates. So this is another line of evidence that seems to indicate that AGB stars are not solely responsible for the interstellar dust mass, dust reservoir. So dust formation in the interstellar medium was then being invoked as a way to overcome this. And people have done experiments in the lab. People have done some modeling. For instance, this paper by Tsukowska et al., who made a simulation assuming grain growth processes, grain shattering processes, various processes that cause that affect the interstellar dust reservoir, and they have different populations of dust here in the solar neighborhood. But if you look at the lines that grow the fastest, it seems that this red line here is the growth of grains in the interstellar medium is the main contributor of dust in this model, and already from very early on. Now, if interstellar dust formation is indeed important, it's interesting to look at the very smallest particles, the nanosilicates, and this is a collaboration that I've started with people here at the University of Barcelona to look at whether we can find these nanoclusters here in lines of sight that probe the interstellar medium. So here is a simulation of some observations that we're currently undertaking on the James Webb Space Telescope, where you see substructure here that is due to these nanosilicates. So we hope to be able to detect them. This panel shows 3% nanosilicates, so that means in terms of silicon, 3% of the silicon is locked up in nanosilicates, and here 10%. So these are the very smallest grains, and we hope to be able to detect it.
Can you say what is actually shown there? So this nanostructure, what is this? These graphs? No, the plots below.
This one. So this is a simulation of JWST observation. So we have 10 and 20 micron here. So this is mid-infrared, and we have this. This is the 10 micron silicate feature, 20 micron silicate feature, and you have tiny little substructure here. You can see it a bit better. That is due to the nanosilicates. A background star through the interstellar medium. So it will be absorption, interstellar absorption. Yes. So we have O and B stars, background stars, and we probe the line of sight towards these background stars. And we hope to be able to find these very smallest building blocks. Yeah. Sorry if that was not entirely clear. So now, shifting gears a little bit, we're going to high redshift galaxies, and I think there too, we can say that the production of dust by evolved stars is smaller than the amount of dust that's being reported to be present in the interstellar medium. And we don't have observations of individual evolved stars at high redshift galaxies, so things are just being modeled and inferred. We do have observations, however, of the interstellar dust masses, or at least the submillimeter emission coming from these kind of objects. So this dates back about 20 years ago when these kind of observations were first coming in, and galaxies were found to be relatively bright at submillimeter wavelengths. And when you fit the SED, the dust masses that were reported at galaxies of a redshift of 6 or more was 10 to the 8 or 10 to the 9 solar masses of dust. And if you actually look at the dust production by evolved stars, by supernovae, AGB stars, you cannot explain this amount of dust at an early time like Z equals 6, which is only 1 gigayear after the Big Bang. So this line, in this diagram here, there are some calculations shown by Morgan and Edmonds of dust yields in different scenarios. So with efficient dust formation in supernova or less efficient dust formation in supernovae, and then of course the AGB dust formation. And this line here, so the problem with AGB stars is they haven't evolved enough to because they're solar type stars, at 1 giga-year after the Big Bang, they haven't reached the stage of dust formation yet. So almost all the dust formation at this early stage is due to supernovae, massive stars. And this red line here is the dust mass reported, and this blue line is the moment in time. So you need to get this amount of dust, and we're order of magnitude away from that. So this was being dubbed as the dust budget problem. And sort of that motivated sort of a line of research that I started, because I felt like, okay, this people working in the high redshift universe are telling me they're finding really high dust masses, and they turn to me as an AGB scientist to explain this dust production, right? And so I went ahead and looked a little bit more in how they determine dust masses. And this is typically done by sampling SEDs. So here you have an example. This is up to 20. This is a relatively nearby object. So this is a well-sampled SED, and you have all these data points here. You can fit a coal dust component here, the red line, quite nicely to this. But still, a single temperature is being assigned to this, and a beta is being fitted, and then a dust mass is being determined. But in some cases, only a single ALMA photometry point was being used, for instance, in this galaxy at Z equals 7.5, where basically the temperature and the beta were assumed to determine the dust mass of 4 times 10 to the 7. And this was supposedly a normal galaxy in as far as that exists at 7.5 redshift. So I was interested in looking in more detail in the systematic effects in these dust mass determinations, because of course it's not a single temperature, and what is the physical meaning of this beta anyway. So together with my postdoc Lapo Fanciullo, we started working on a model grid of mock galaxies. And when I say mock galaxies, I basically mean a population of dust, because I don't care about anything else. I'm just fitting the cold dust component. So my galaxy is just a cloud of dust. We put in, for now, we just put in a single or 2 temperature dust populations, just to start out simple. But ultimately, we want to put in a temperature distribution. We used laboratory measurements of temperature-dependent dust opacities, because we did find some that were available, but that are not being used in these kind of determinations. We apply a redshift, so we put it at some redshift. And then we determine the synthetic photometry for various instruments, and use that synthetic photometry to determine a dust mass using commonly used methods. And we compare the derived dust mass with what we know we put in. Yeah. So what did we find? So first of all, let's have a look at the systematic effects that already exist in the dust opacities themselves. So this line here is a typical opacity that people use to model, but we used some measurements from the lab. So from Manella from '98, and also from a group in France here, Karine Demick and Coupeau here as well, who have done some more recent measurements. And you can see that this thing is dying. What you can see is that these lines are all measured at different temperatures. So you see that the dust opacities are not, in fact, constant, but they vary with temperature. So the lowest temperature is here and the highest temperature is there. So if your dust has a different temperature, you have to multiply it with a different dust opacity. And also, typically, they lie significantly above the assumed dust opacities that people use. So this is the standard mixture that we made. So we made a mixture of roughly 70% silicate and 30% carbon. This is what people seem to be using, looking at these distant galaxies. And we looked at 2 different temperatures, 100 and 30 Kelvin. So this is all based on these literature values, these laboratory values of opacities. And these lines here at the bottom are various dust opacities that people have used to determine dust masses in the interstellar medium of high redshift galaxies. So you can see we are above that. The slope seems to be roughly okay, although not in all cases. Yeah? Then we actually did a single temperature fit for synthetic galaxies, which has a dust reservoir at a given temperature that we call temperature real. So the real temperature is here plotted at the bottom here on the horizontal axis, and then on the vertical axis we have we show the ratio between the fitted mass and the real mass that we actually put in. And then we have done this for different redshifts. And what you can see, and here is the summary plot, that we are at least a factor of 10 over in dust masses by using a conventional method of determining dust masses. So this is very worrisome. In some cases, it's even much more. We also looked a little bit into this idea of just doing a single temperature fit. Which is what people seem to be doing because they have so few data points. So basically, you're not deriving the temperature of the dust, you're deriving something like an effective temperature, which may not have any physical meaning. And we try to look into this by making our synthetic galaxies have two temperature components, 100 Kelvin and 30 Kelvin, and mixing them in different ratios. So that's shown here. On this axis is the fraction of the warm component in the overall dust mixture, and then you get for different warm fractions you get these different SEDs. So you start with the lowest warm fraction. Here is the highest warm fraction of 0.3. Your SED starts to look more and more different. And if you start fitting a single temperature, which is what we've done with this red curve, you see that the single temperature gets higher and higher, which is, of course, what you expect. But it's not a physical temperature. And then if you start deriving dust masses based on that, you get still an overestimation, in this case, of a factor of about 5. So yes, I already made this point, but if you are trying to fit a single temperature to an entire galaxy, you are basically fitting an effective temperature, but in reality, you're having a mix of temperatures, of course. You're mixing different dust populations. You have warmer dust in star-forming regions and colder dust in regions where there is no star formation. And even within regions, there is, of course, a gradient in temperature. So yes, here, I mean, this is just illustrated here. Of course, you can fit an SED that is composed of two different temperature components with an effective temperature. But because the black body curve is so strongly dependent on temperature, your dust mass that you derive is very sensitive to what effective temperature you end up getting. And this is also demonstrated by actual observations. So again, going back to our SAGE survey, so in the beginning, when we first got the Herschel data, we observed the LMC in 5 strips like that. But our first lot of data was just the central strip. So this this analysis is only done by on a strip in the LMC. So here is the highest resolution observation that we have. But what Frederick Galiano did was he actually deconvolved, or he merged together pixels in larger and larger groups until he basically put everything together to sort of emulate this idea of mixing dust populations in an entire galaxy. And then, so you are seeing the same dust everywhere, but he determined the dust masses, he added up what he was getting, so for the pixel-wise fitting, and he found that there is a dependency here. So if you average everything together, you get a lower dust mass than if you start separating out star formation regions and so on. So this is already a demonstration that it matters what you do. And I plan to do, this is something that's future work, but I plan to do more work on this, both observationally, similar to this, and modeling, where we are going to use mock galaxies to approach this. Then finally, the topic that I'm currently working on is to actually calibrate these far infrared and submillimeter opacities. And I think that nearby AGB stars, so I'll introduce a new survey to you, provide an opportunity to calibrate opacities in the submillimeter against the infrared. So the idea is, you've seen this slide before, that we're going to be looking at nearby AGB stars, which is the reason that I put this plot in. So this is the distribution on the sky of the nearby AGB stars. And like I said, they're isolated, bright and dusty objects, so you can easily pick them up in many surveys, and we've combined all the data together. We assume spherical geometry and constant outflows. The constant outflows are important because we actually put together a sample of about 850 objects. So again, we compared them all with this model grid that we had. And for each mass loss rate bin, we went out to a certain distance to ensure completeness. So we divided our sample in 4 mass loss rate bins and went out to a certain distance to get roughly equal numbers in each bin and ensure completeness out to that distance. And we ended up with a sample of 852 nearby evolved stars, which we then observed with the James Clerk Maxwell telescope with SCUBA 2 on this, and also the heterodyne instruments, to get submillimeter continuum and CO line fluxes. And the submillimeter continuum will be used to study the dust emission. So here is a slide introducing the NEST survey to you. So these are the key questions that we want to address. So we're interested in determining the total gas and dust return to the ISM, looking at gas to dust ratios and stellar outflows, looking at the mass loss history over time through spatially resolved observations, but also here this constraining submillimeter dust properties, and that's the topic of what we are talking about now. So let's continue on that. So in our earlier work on this data, we already found that there is an anomalous coal dust reservoir, and that I'm showing this figure again, and that comes down to an under-prediction of the real observations at 450 and 850. So if you fit your spectral energy, again, it's not working. If you fit your spectral energy distribution using dust radius transfer modeling, and you basically end up making a prediction here at these longer wavelengths, you can then compare that with what we get from 450 and 850 at SCUBA 2, and we find that the observations are systematically above what we predicted. And here in this diagram, we also see that. So here is the dust mass, and you see that this is for a single object. We see that the dust masses are also higher in sort of the radial profile as well compared to the predictions. So if you look at the entire sample, or the part of the sample that we had when we put out the overview paper last year, you see that the excess of 850, this line is 1 here, is seen in virtually the entire sample. There's only a few objects that lie behind this ratio 1 line. So we have a systematic or an under prediction of what is really happening. And this is true across the entire range of dust production rates, especially at the higher dust production rates. So we will use this data to actually recalibrate the far infrared and submillimeter opacities. And that's work currently in progress. I'd hoped I would be able to show you more about this, but it's really very much in progress. So, stay tuned. So are we then overestimating interstellar dust masses? Because if we think we see all the dust in these AGB stars and we have to revise the opacities upwards, then that means that we might actually have less dust in interstellar environments than we previously assumed. So just to recall, this is the picture that we had. The dust opacities that people are typically using to fit are sort of on the lower end of the available values in the literature. It's also good to bear in mind that dust opacities are not well characterized at far infrared and submillimeter wavelengths, and so far they've not been calibrated against mid-infrared opacities, and that's what we're doing right now. So we hope to fix this. Also, people are typically using locally derived opacities for everything, but it's clear that locally derived dust opacities do probably not apply everything. Dust is different in different environments, and here is just Here is just a slide demonstrating that, the zoo of dust that we see in quasars, in fact. So this is something that I've looked at as well in the past. Here you see silicate emission from a particular quasar, but you see a lot of substructure that indicates that there are other dust components present as well. And we looked at a larger sample a few years ago, and actually there's a whole range of possible compositions. So here are the compositions, here are the species. You see a whole range of compositions in different quasars. So clearly dust is not uniform along across the universe. And this diagram shows that dust formation actually can occur in quasar winds, because the dust formation zone that you see in AGB stars, which is this shaded area, actually coincides with the regime that is seen in quasar winds in this temperature density plot. Okay, so going back to this slide, we also have systematic effects due to limited photometry points. I said that the SEDs are only have a few points. We drive a effective temperature. What can we learn from that? So there are some systematic effects. These need to be better characterized. So we did a little bit of that, but we've only scratched the surface. We don't really know yet which direction this is going in. A more detailed analysis is necessary. And but the things so far that we have discovered is that there seems to be an overestimation of the interstellar dust mass by about a factor of 10 using the current methodology. And then, of course, this has implications, especially at high redshift, where you only have these submillimeter data points to measure the interstellar dust content. And so if you overestimate the interstellar dust mass, then you might also overestimate the interstellar gas mass because you have no other traces, and therefore the star formation rate. This is, like I said, this is especially true for galaxies with only long wavelength photometry, and it especially affects deep field surveys where you have only this limited amount of information. If you have individual galaxies that are well studied, you can maybe overcome this, but it's quite expensive. But having this lower star formation rate potentially has far-reaching consequences for our view on galaxy evolution. So this is something that we have to really look into a bit more. Well, I plan to do some future work in the calibration, like I said, the calibration of the submillimeter and millimeter opacities against the what's going on at the infrared. So that is currently ongoing. And also with my former by now postdoc Lapo Vantulo, we continue to work on this model grid of galaxies to figure out the effects of systematic effects in this temperature and beta fitting. And here is some plots produced by him showing the parametrization of opacities that we're going to use for that. We also want to use or can use. There's a wealth of data available, especially from the JCMT. So we want to use this data. Surveys of nearby galaxies, for instance, Andromeda here, where Scuba 2 map is made at 450 and 850 of the entire galaxy. There's a whole a host of other galaxies that are being targeted. But also there are other surveys, cosmology surveys in particular, operating at longer wavelengths that end up measuring interstellar dust, the thermal emission from interstellar dust. So we can use that as well to further calibrate things. So for instance, the South Pole Telescope here has put out a paper showing this map of the SMC and the LMC as well. And this work will then complement studies on the dust production to compare. And also further down the road, a new development or a new initiative is this ATLAS single dish telescope, 50-meter single dish telescope, which is going to operate in the millimeter and the submillimeter. It's going to be placed in the southern hemisphere, so the Magellanic Clouds will be accessible. It has a field of view of 2 degrees, and currently a study is underway into the feasibility of this project. But this diagram shows where it sits, so this is in time, but where it sits in terms of field of view on this axis and primary mirror diameter. So it has a smaller field of view than FEAST, which is being planned for a few years from now. But FEAST, which is sitting here in terms of the diameter of the primary mirror, it's much smaller, and ATLAS is more comparable to the LMT. So the idea is that ATLAS will be operational in 2030. So this sort of work will be a very suitable to carry out with ATLAS. Then to conclude, so I want to highlight that the reported interstellar dust masses are too large to be due to AGB dust production as we see it today. So that could mean a number of things. One of them is that there is another source of dust, for instance, ISM dust production. But another implication could be, or another explanation could be, that the interstellar dust mass determinations in the far infrared and submillimeter are actually inaccurate and need to be revisited. And if they are inaccurate and we have to revise our dust capacities at these wavelengths to higher values, this has implications. And it means that the dust masses in the interstellar medium of galaxies have to be revised downwards. So does the star formation rate, which has then its effect on galaxy evolution. It also has implications on our understanding of star formation processes. I mean, if we study a region of star formation and ultimately there is less dust presence than we thought there was present before because of the lower opacity or the higher opacities, we have to revise our understanding as well. But on the positive side, it gives a much more natural explanation for the dust cycle in the local universe, and maybe there is no need for extensive ISM dust formation after all. Thank you.
Okay, it's time for questions.
So you only very briefly mentioned the role of supernovae in producing dust. Is this a well understood phenomenon? I remember seeing a talk by somebody, and I couldn't remember the name anymore, but claiming that actually supernovae are a surprising efficient contributor to dust production.
Yeah, so it's something that we should also take into account. The problem with surveys like, so there's a number of different things to this. The problem with surveys like SAGE, for instance, where we add up the production of dust by AGB stars, is that we have 40,000 or so AGB stars. So you can that's a good number to work with. You can do statistics, you can add them up and determine dust production rate. Yet the number of supernova remnants for which you can reliably determine the dust produced is very low. So it's not so easy to determine dust production rate. And then I think, well, people say different things, so some depends on who you talk to. But I think we have trouble establishing what is really the efficiency of dust production in supernovae. But then supernovae must form dust because they are found in pre-solar grains in meteorites. So we know it forms dust, and we just haven't quite put a finger on how efficient it is, or if it is efficient, how efficient the shocks are in destroying it again. So yes, it's a very complicated matter, and the observational the observational data doesn't really help us as much as with AGB stars. Yeah.
Thank you, Siska. So yeah, I'm a little bit surprised that you say that the two hypotheses are kind of equal standing, because so for example, if you say that the interstellar dust mass is generally overestimated, right? I mean, but this would be true also in the Milky Way.
Yes.
So I thought the Milky Way amount of dust is fairly well determined, at least well in the solar neighborhood, right? I mean, we have a lot of ways, right, to investigate how much dust is there in the interstellar medium from extinction studies and all that. And so whereas on the other hand, dust production, what I hear generally is there's many possible mechanisms and there's many other possible contributions, right? AGB is just one of them. I mean, even in star formation, right? When you form stars, you have all these huge disks that are then blown away. So aren't there many different ways to form dust? Also in active galactic nuclei, for example, we know there's obscured
dust, yeah.
active galactic nuclei. They form dust very quickly,
yeah.
right?
So yes, so ISM dust formation is probably not the only source of dust. So actually, you can make a table. Now you have AGB stars, you have supernovae. We already talked about that. You can also have dust production by material that is being ejected by YSOs. You can have different things, and there's also ISM dust formation. I'm not saying that they are really on equal standing here. It's just that I think it's not entirely clear yet. And even when you say, well, we know how much dust there is in the Milky Way, I'm not convinced that we do know. I mean, we are observing towards background stars, and we are measuring extinction, sure, but you're only probing that sideline to that star, right? Whereas if you look at thermal dust emission, you look at the entire cloud. So you have to somehow calibrate these two things. You're not probing the same volume. So I'm not convinced that we have calibrated this well. Yeah. It's dangerous to say that here, no?
No, it's just a question in this context. As far as I understand, in the solar neighborhood, for example, for us, when we were working in the galaxy model, based on galaxy model and so on, the dust volume dust density we have is not as well understood as I know. So it's not something that we said this is understood in the solar neighborhood and the volume dust density is such, because this is very important just to understand the amount of dark matter when you're looking the dynamics of the stars. So one of the important points of uncertainties is just this volume density of dust and gas and so on.
Yeah.
My as far as I understand, I don't know. The other point is about the AGV, the AGV dust production. You are modeling assuming some models, no? Sphericity, constant flow, blah blah. The binarity is not playing any role.
No, we haven't taken that into account. No, but I guess we should. Yes.
No, it's just a question because it's always the same problem. No, but I don't know if at these wavelengths, if it is a problem for you or not concerning the type of binaries you have in these objects. Companions.
Yeah, so I haven't really given that much thought. It's clear that what we've done is assumed, that these are single stars, but we do know that some stars are binaries, even stars undergoing mass loss. So there are some nice pictures of these spirals, and one of the leading theories for that is interaction with a binary that actually kind of sculpts the outflow in showing a binary. But of course you can have, I'm just thinking now of the cuff, no? You can have many configurations when you're talking about a binary, and maybe in some cases the binary causes the AGB phase to truncate, and you might not have mass loss at all, or it might also be, I don't know. So I don't know how important that is. But on the other hand, if we are looking at the LMC and we have this observational data point where we see all these, we can identify which are the AGB stars, and we measure the dust production by them. Those are the AGB stars that actually make it to this phase where they can produce dust and deposit it into interstellar medium. Maybe there are more, but due to the binary interaction, they cannot efficiently form dust, perhaps. But our observational point is the ones that actually make the dust and deposit it in the interstellar medium. So observationally, I think we have a good handle on how much dust makes it into the interstellar medium, I think, yeah. Yeah.
Regarding the Magellanic Cloud survey, we have seen the dust maps separately on the LMC and the SMC.
Yes.
But do you make the connection between them to trace the breach in dust?
In our survey, the connection was not fully mapped. No. It's partly mapped. So, one of the plot that I showed there is you see a tail.
Because you see the tail, the beginning of the bridge from the SMC, but I would like to see if there is the connection.
No, it's not fully mapped. No.
Thanks for the talk, Siska. So I have a question. If I got it right, so for this ISM dust production, there were these nanosilicate particles that you were mentioning.
Yeah.
And my question is, where is this silicon coming from? So my understanding was that silicon in the ISM conditions would be trapped as refractory material in the dust grains, but to have these nanosilicate particles, so you have some silicon outside the dust grains?
No. So actually what's happening is I showed you this theoretical calculation where you produce just about the amount of dust that is present in the interstellar medium today. Also, there are other simulations that show that on average dust grains, or the dust lifetime, is about 1/10 of the residence time in the interstellar medium. So dust is being destroyed and reformed, and this all the time, and this happens due to shocks traversing the interstellar medium. And actually you see this, behind the shock you do see silicon oxide, you see this behind where a shock has just traversed to, you see this kind of species in the gas phase. So if a shock has traversed to a region and has evaporated or spotted all these grains into oblivion, you have these building blocks again to start forming silicates again. And then the idea is that one path is that it goes through this step of nanosilicates. If you have reduced the silicates really to the elemental building blocks, if you still have some cores left, then you can also just grow by grain growth, by sticking and
And the time scales to go from these nanosilicates to normal grains after this shock passage, for example. So it's short.
Yeah, I haven't looked into that. I don't know.
Thank you.
Yeah. Many questions.
Hello. Yeah, sorry if I missed that, but what is the physical meaning for the beta parameter? Because it seems it's a very important parameter, but I don't know if you mentioned the physical explanation why it changes and yeah.
No, it's just a description of the opacity. There is no physical meaning.
So it's not a grain size.
It's just that it's you can change the slope of an SED by making larger grains, but that does not inherently change the beta. So the beta is just a property of the grain. So it's the bulk. It's just a description of the opacity of the bulk material. So there is not really a physical meaning to this. So this is another problem that I have with this beta. that it's not really, it doesn't have a physical meaning. But maybe you disagree.
Well, I would like to point out that when people doing protoplanetary disk, beta is a key parameter for grain growth. For grain growth. So small values of beta, they imply, or they assume that it implies that you have grain growth in the disks.
Yeah, but then it's no longer an opacity. Then you have changed. I mean, if you just take this as the bulk opacity, then you have to add another power law to
It means that
you change the power law. Yes, of course, yes. But the beta itself, if it's part of the opacity, it doesn't have an inherent meaning.
Hi, thank you for your talk.
Yeah.
Just a question about at last. You say operational in 2030.
Yeah.
And I would like to know what is it, if it is commissioning or already open for other observers.
Oh, we're still in the study phase, so it's.
So maybe first slide, maybe in 2030.
No, it should be operational. That's the current plan, But we're still in the study phase. We're doing. We're investigating the site. We're looking into energy use and that kind of thing. So it's still early days. There's only funding right now for the study phase, and then it really depends on whether we secure additional funding. But the idea is it should be operational by 2030. That means indeed science operations. Yes, that's the hope.
Okay, there is time for one more question or comment. Okay, Casus.
What is a strategy for modeling this Mars temperature dust in distant galaxies? Because SMC or LMC are different from those galaxies in terms of, and even in distant galaxies, ULAGs like up to 20 have a very compact core of star-forming region, and the submillimeter galaxies much more extended region of dust. So I think, and what is the exact strategy for building a modeling?
So I think this is still a work in progress. I think with distant galaxies in particular, you cannot avoid, I think, that you have to determine something like an effective temperature. So what we really need to understand is what the systematics are by, having to use an effective temperature. And perhaps we can figure out whether we need to fix a certain beta, or that we suggest which opacities to use or whatever. But I think this is still subject of further study. I think right now it's looking a bit hopeless, I think. So we really need to understand what the systematics are, which direction they go in, and how well we can actually determine the dust masses. And then we can decide on a strategy. I think that would be my answer to this. So work in progress, at least from my perspective. Yeah.
Okay, if there are no more questions or comments, well, let's thank Francisca again for her nice talk, very nice colloquium. And thank you all for your attendance. See you next time.